Hey there everyone, this is Hanson once again. Welcome back to our lessons in Chapter 5 on stereochemistry. We're picking up thinking about enantiomers, those non-superimposable mirror images of chiral carbons. Some stereoisomers are classified as enantiomers, and we just want to be sure we see this definition. Two molecules that are mirror images but are not superimposable on one another, just like your left hand and your right hand, are enantiomers. Your left hand and right hand are indeed mirror images, but they are non-superimposable, meaning when I took my two palms and just lay the hands both face up, you can clearly see that they are not the same, although they are mirror images. So let's take that into the chemistry world, and notice here we have a 2-chlorobutane. 2-chlorobutane has a chiral center. We understand that a chiral center is a carbon that has 4 unique attachments. So not drawn, but clearly knows is there, is the hydrogen behind the chlorine. When we draw its mirror image, imagine the reflection, carbon 1, 2, 3, 4, and off of carbon 2. Kind of thinking back here, ends up to be the chlorine. Looking at the mirror image, just kind of thinking in terms of what is closest to the mirror, ends up to be carbon 4, there's 3, there's 2, there's carbon 1. By placing a mirror next to the chiral carbon, the molecule itself, and drawing the mirror image, we now have understood that we have the mirror image called its enantiomer. I just was thinking that we could definitely prove to ourselves in order of spin. You know, let's say the highest priority by atomic number would be chlorine. Chlorine is priority number 1. A carbon connected to a next carbon would be priority number 2. And of course, a carbon attached to 3 hydrogens would be priority number 3. So as I look at the rotation of the 4 attachments, I need 3 numbers. The 4th priority is in the back. We're spinning in a clockwise fashion. So we're learning that that is the R designation. So the rotation around the chiral center is the R. Now let's just compare that to what's happened in the mirror image. Remember again, the chlorine is the top priority by atomic number. The next priority is the carbon attached to another carbon. And then here the carbon attached to just 3 hydrogens. This time when we spin, we get a counterclockwise configuration, and we're learning that this would be the S designation. So these are indeed 2 different molecules. They are enantiomers, non-superimposable mirror images. This would be known as the S configuration of 2-chlorobutane. And so since every unique compound gets a unique name, the R and S will become part of the nomenclature around the chiral carbons. So we've just drawn a mirror image, and that mirror image is known as its enantiomer, a chiral compound drawn in a mirror. Often it's just easier to draw the enantiomer of a chiral compound and simply invert the dashes and the wedges of the chiral center. Notice here we have a chiral carbon at position 2, 2-chlorobutane, just as the previous slide had shown us. And I can quickly invert it, not by drawing a mirror image, but keeping the chiral carbon in the same position, but instead of a dash, simply draw its wedge. Now prove it to yourself that this really did change the configuration. Notice that chlorine is priority number 1. A carbon attached to 2 other carbons is priority 2. And then here, priority 3. We labeled this the R configuration. Now remember, what happens here is that the priority is now the dash. It's like walking behind the molecule. The hydrogen is the wedge, the chlorine is the dash. And so now the lowest priority is actually staring behind the page. And so you're looking at the molecule like walking around and seeing its other side. By the time we're done looking at this priority, priority 1 is in the back, priority 2 to the left, priority 3 over to the left side of that chiral carbon. You might think that we're still spinning in that clockwise fashion, But remember, the hydrogen is coming out to you. So when priority number 4 is the wedge coming out, you're standing on the wrong side of the molecule. So flip your answer. Walk around that molecule so the chlorine now is coming out of the page and the hydrogen is closest to you, and you'll see that you actually now have the S configuration spinning counterclockwise. We're going to have so much more practice that. I'm just kind of leading into that, knowing that enantiomers spin their priorities in opposite directions, clockwise and counterclockwise. We can draw the mirror image, and so just as we did on the previous page, if this is the original compound, I can certainly draw the mirror image. And when I do so, I've created the opposite, or enantiomer, the opposite rotation. Or we could simply draw the molecule as it is and change whatever is a wedge to a dash, and we've accomplished the same thing, that these are indeed the same molecule. So, in a pair of enantiomers, from the chiral carbon, we switch what is the dash and what is the wedge to find its non-superimposable mirror image known as the enantiomer. Here is the chiral carbon. 2 of the bonds are in the same plane. That's always the truth. And then over here, as a dash, we had a hydrogen, and as a wedge, we had a methyl group. Now all of a sudden, the methyl becomes the dash, and the hydrogen would become the wedge. These are enantiomers. Now remember, to have an enantiomer, you must have a chiral carbon. That is not a chiral center because we have 2 attachments that are indeed the same. So to meet the criteria to have an enantiomer, you must have a chiral center. And just proving yourself that any mirror image can be drawn in several different ways, you can place, for example, the mirror behind the molecule. And this is what we were just looking at. When I place the mirror behind, notice that all the dashes convert to wedges and vice versa. All the wedges would convert to dashes. And that's simply by walking to the opposite side of the molecule and looking at it from the other perspective. So when I draw the enantiomer with the mirror behind, the wedge that was here converts to a dash here. You can place it next to the molecule, as in this situation, and I literally just put up the reflection and draw it as it is, the closest things to the mirror, and then work your way out to the mirror. And of course you can draw an enantiomer from placing a mirror under the molecule and just literally flip the direction of things that you see. So at this position we went up, down, up. Notice we'd go down, up, down, but I still maintain the wedge turning to wedge. So you just have some different perspectives to draw enantiomers depending upon what you want to accomplish. The easiest, perhaps, is to just take the molecule and redraw it as is and just convert any dash into a wedge and vice versa. If the molecule is simple enough to draw as a mirror image, this would accomplish the same task. So let's practice. Let's draw the enantiomer of each of the following compounds. I just grabbed one from your homework. Notice I have a chiral center, notice with the stereochemistry drawn at the carbon I highlighted red. Since this is a rather complex molecule and the stereochemistry is shown, I think I'll just draw it as is, exactly as it appears on this side of the molecule. Leading out, I have the stereochemistry drawn exactly the same until I get the dashed hydroxide. I'm going to convert it, I have the wedge hydroxide, I'm going to convert it to a dash. Sorry, I misspoke there. That is an enantiomer, redrawing the structure and just simply replace the wedge with a dash. Non-superimposable mirror images. Another one from your homework that didn't give us dashes and wedges. We have a bicyclo compound. We practiced naming those in chapter 4. The bicyclic compound, where we would find the 2 bridgeheads and count the total number of carbons. In this total number of carbons, we have 1, 2, 3, 4, 5, 6, 7. So we know that that is a heptane. We know to use the bicyclo, and we know to leave little brackets in there for numbers, right? And so when I think about what those numbers stand, how many carbons separate the two bridgeheads? In one direction, there's 2 carbons. In the second direction, there's 2 carbons. And in the third direction, there's 1 carbon. So we had 2, 2, 1 in terms of the numbers. And then remember, carbon number 1 leading to the substituent to give it the lowest number. So that would be 2-hydroxyl bicyclo, 2,2,1 heptane. So just a little practice from chapter 4. I digress, sorry. But here we're asked to draw the enantiomer. And so at this point, it might be just easy if we were able to just draw the mirror image as best we can. And this is where I get challenged. I'm going to draw the mirror image. Here is this leading up, then back down, and then this carbon attaches down and then up. Can you draw a cyclohexane better than I can? I'll try again. There's my 2 sides. I help my 2 dots to help me, and then here's that best I can, although that's a ring flip. I'm really sad. This is what I'm really trying to draw. And then on the mirror image, the OH here, the H of course would be here. And this is me trying to draw that in a mirror image. Thank you for your patience on that one. So that's all I would be able to do in my Wiley, for example. It's so much easier to draw on Wiley because it connects for you. But when you don't see the stereochemistry, just as in this bicyclic compound, I'd recommend just drawing the mirror image, and then you know you have the enantiomer. So one choice, flip all the dashes to wedges and vice versa. Or choice number 2, draw the mirror image, especially if no stereochemistry is given by dashes and wedges. We've been alluding to this section all chapter long, how to designate R and S configurations and then include them in the name to give every compound a unique name. We use the Cahn-Ingold-Prelog system to designate each chirality center as either having an R for a right-handed spin or an S for a left-handed spin, clockwise or counterclockwise spins. If the R configuration at a chirality center, its enantiomer will have the S configuration. The reason we use S is it's from the Latin term of sinister, which literally means left hand. It's Latin for left. So sinister S, R for right hand clockwise and counterclockwise spin. And remember, the highest priority is given to that with the highest atomic number. And we're going to practice this. The next priority and then the lowest priority always put in the back, which here would be the hydrogen, lowest priority. And so when we connect those, we can see that this direction would have an R configuration, a clockwise spin. But let's take that step by step and keep practicing till we feel proficient. So we use atomic numbers to prioritize the 4 groups and attach them to the chirality center. Now, priority number 1, the highest priority is given to the highest atomic weight. The next priority would be the second highest atomic weight. And then priority 4 would be the least, usually a hydrogen, the lowest atomic weight. So when we designate highest priority, number 1, remember that this is the highest atomic number, which corresponds to atomic weight as well, highest atomic number. And then this, of course, would be the lowest atomic number. The highest priority, highest atomic number gets the number 1. We want to arrange the molecules in space so that priority 4, which is the lowest priority, is always behind you. So you want to look at the clock, if you will, of priorities 1, 2, and 3 and decide, are they spinning clockwise or counterclockwise? So here, for example, just by prioritizing, and we see that the going behind dashes are behind the page for the highest priority, we need to rotate that always to ensure that the lowest priority is behind you. That's the critical step to get the correct confirmation. Is it R or S? Number 4 has to be behind the page. So again, if we look at the lowest priority behind the page and it's spinning in a counterclockwise fashion, we'll call that an S configuration. If we're spinning and the lowest priority is in the back, as we need it to be, and it's going in a clockwise configuration, a right-handed spin, it will get the confirmation of R. Priorities are assigned based on atomic number. Highest priority is number 1, highest atomic number. The lowest atomic number, lowest priority, that gets the number 4. Position 4 needs to be behind the page in order to make a choice of R or S. Well, let's practice one. Here is a chiral center. The chiral center has 4 branches. So this is the chiral center. I see one of those of the 4 bonds is a hydrogen. Another of the 4 bonds is a hydroxyl. Another of the 4 bonds is a carbon chain. I see a CH2, CH2, right? CH2, 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 and then a CH3. 1, 2, 3, 4, 5. So this is a long carbon chain finally terminated with a CH3. I'm only going to say I can see a point of difference coming up here soon. And then the opposite direction, I see a CH2. And then I see a point of difference from the right-handed direction. I see this carbon is now attached to 2 other carbons. And so we'll have a point of difference. And let me kind of clarify what I mean there. So let me erase this and kind of really expand on what a point of difference means. In our chiral carbon, let's compare those 2 positions. Alrighty, chiral carbon leading out to a carbon. What is this attached to? Well, it's attached to a carbon and 1 hydrogen and 2 other carbons. Notice how I listed those in terms of priority, highest atomic number, and worked my way down. This carbon has 3 attachments, right? It's leading from the chiral carbon. This carbon right here is attached to 2 hydrogens, and this is attached to 2 hydrogens and a carbon. They are exactly the same, so therefore there's no point of difference. We had to go to the next position to actually identify the priority. And so that's where we're practicing R or S configuration. Keep going. If we have a tie, keep going until you find a point of difference. This molecule, or this carbon and this carbon, are exactly the same, so keep going. Here's another CH2. Oh, see how this carbon in the next position, it's not a CH2. This carbon here is attached to 2 other carbons, so we're going to see that it will receive priority. All right, so let's kind of really dive in to get comfortable with that order of priority. So again, here's a chiral carbon. I can clearly see that this is a top priority, the oxygen, highest atomic weight, number 1 for priority. Here I clearly see that hydrogen is a lowest priority, nothing smaller in terms of atomic number 1, so it's always the lowest priority, so it's assigned a 4. When I go 1 carbon out from this chiral carbon, I see a tie, that there's no point of difference between a CHH to the right and a CHH to the left. They're exactly the same. So it's a tie right now yet for priority 2 and 3. So I'm telling you, keep going down the chain until you find a point of difference. Now we're comparing the carbons that are 2 carbons away from the chiral center. This carbon is attached to a carbon, carbon, hydrogen, carbon, carbon, and a 4th bond we don't see, but an H. This carbon is attached to 2 hydrogens, CHH. Clearly we see a tiebreaker where this side now is of higher priority. So this carbon would become carbon 2 for priority, and this side would become carbon 3. So we're emphasizing when assigning priorities, keep going until you find a point of difference to determine the higher priority. And friends, remember, if you never find a point of difference, it was not a chiral carbon, because there must be 4 unique attachments to be considered chiral. So our answers were really thinking about, is this an R or an S? I keep showing the same molecule without, I'm kind of just getting us to an answer. Is it an R or an S configuration? Well, I know that we've decided that here's the chiral carbon. The hydrogen was priority 4. That's a 4. Here we had a dash to the highest priority, and then in the same plane we had priority 3, priority 2. So this is kind of the setup of that chiral carbon. Priority 1, hydroxyl group. Priority 4, that was the hydrogen. Priority, the next highest would have been this carbon attached to a isopropyl ring here, right? And then over here we had a straight chain, so that was the 3rd priority. So do you see what we have in terms of our representation of 1, 2, and 3? Let's kind of color code that to be really clear. Priority 4, I'll highlight in yellow. That's the hydrogen. Priority 1, I'll highlight as hydroxyl. Priority 2 is this carbon chain. That's the 2. And then priority 3, color coding, is this carbon chain. So I have 4 priorities. But remember, before I can assign the R or S configuration, priority 4 must be in the back. And right now it's coming out at me, right? The hydrogen is a wedge. We want it to be a dash. So what do? Let me introduce to you something called the swap rule. It is going to help you so many different ways. The swap rule says, if I swap one set of bonds, it will give me its enantiomer. If I swap 2 sets, it gives me the same molecule back. And if I swap a 3rd time, it gives me the original enantiomer. Let me tell you what I'm saying by modeling up here. Keeping the color codes, I'm going to put back and I'm going to swap 1. What I mean by that is, let's swap priority 1 with 4. So now all of a sudden, priority 1 is going to become the wedge. Priority 4 becomes the dash. And these guys stayed the same. So swap 1 says you're only allowed to swap 2 bonds. Break number 1, break number 4, and swap their place. Now, remember, this is the original. So swap 1 says this is the enantiomer. Every time I swap, I know that I've created, each odd swap is the enantiomer. And so I want to know the original molecule, right? So I can go back to the original molecule with a second swap, swap number 2. Well, I wanted the lowest priority in the back. I've got it. That's the hydrogen. I want the hydrogen to be in the back. So that's not what I'm going to swap. I'm going to leave number 1 and 4 the same. So the 2 I'm going to swap this time are attachments 2 and 3. So in my first swap, I swapped 1 with 4. In my second swap, I'm going to swap 2 with 3. And now what have we done? We've got back to the original molecule. This is called the swap rule. Odd swaps give enantiomers. Even swaps get you back to the same compound. I like to just assign configurations of 1, 2, 3, 4 as I'm swapping, and then I can go back to the original molecule to draw it. So what do I have? This carbon, that's the chiral center, now has the priority labeled 1, which was green, as the hydroxyl group. That's the OH. And the priority labeled 4 was the dash. Priority 3 was this 1, 2, 3, 4, 5, 6 carbon chain. And now, so I would just have it 1, 2, 3, 4, 5, 6 carbon chain. And then priority 2 ended up bottom, and that of course was the carbon leading down and then up and with the tail. So that's how it ended after 2 swaps. And when I swap this, I can clearly connect my numbers 1, 2, 3 to find that this is an R configuration. I swapped once to get the enantiomer. I swapped twice to get the original molecule back. 2 swaps allowed me to get the lowest priority in the back. The highest priority came to the front, and I found a clockwise configuration, an R. Now, all of those swaps allowed me to get back to the original equation, right? So that's what we did. We swap once. If this is the original, if my first swap, I want 4 in the back, so I always swap to get 4 in the back. However, that's the enantiomer. It has the opposite configuration of what you want. So you do a second swap, and now you're back to the original conformation. Now, the swap rule allows you to really just quickly go and decide, is it an R or S configuration? Here we have a chiral center, and we're just being asked, is it an R or S? We're practicing recognizing that the top priority is the highest atomic number, so the hydroxyl is the top priority. It will be number 1. The lowest priority is assigned to number 4. The smallest atomic number here is hydrogen, the lowest priority. We move out to this direction. These are both carbons, and so we need to find a point of difference. This carbon is attached to an oxygen. This carbon is attached to 3 other carbons. And so the tiebreaker gives the higher priority to a carbon attached to an oxygen because that's a higher atomic number than a carbon. And so this now gets priority number 2, and this is priority number 3. If you find color coding helpful to you get good at this, priority 4, that's going to be yellow. Priority 1, we'll color code green. Priority 2, how about this nice blue? And then here we have priority 3, that carbon chain. All right, now in order to configure R or S, the lowest priority has to be in the back, and it's not right now. So here's my chiral carbon. Right now what I have is priority 4, 1, 3, 2. That's what I have. Now let's flip once. Do one swap. I want to swap 1 with 4 so that when I do so, I can get number 4 to the back. So let's swap out. The wedge becomes number 1 and the dash becomes number 4. 2 and 3 are still in the same plane, but this is the enantiomer. It is the mirror image, non-superposable mirror image. It has the opposite conformation of what you want, enantiomer. So we need a second swap to get back to the original conformation. I want to leave 1 and 4 exactly how they are because that was the purpose of moving them. But the next swap I'll perform will be swapping 2 with 3. When we swap 2 with 3, we're back to the original enantiomer. Original, I tried. Now what do we have? We're ready to spin. We have 1, 2, 3. We connect those numbers. It's an R configuration. It's spinning clockwise. You want to know a shortcut? Watch what happens. This is exactly the same thing but easier. I notice priority 1 is in the back, priority 4. If that happens, this is okay to do. Just go around the molecule, look from the other side. Still, I have the attachments where 2 and 3 give me that spin. If 1 is in the back and 4 is coming out, watch the trick. Notice when I connect the numbers, I have an S configuration. This means what I'm looking at is from the opposite direction. So just flip your answer. And done. You now know that that's an R configuration. Let me repeat that. In a very special case, if you notice, priority number 1 is a dash in the back. Priority number 4 is a wedge in the front. The easiest thing to do is assign priorities just like you normally do. Here's 1, here's 2, here's 3. When you connect those, I see that's a counterclockwise spin, so I might be tempted to say S, but I'm standing on the wrong side of the molecule. To make the dash become a wedge, walk behind it. And what would you see? You would see the opposite spin, so flip it to an R. The swap rule gets me the same answer. Or when I notice that the lowest priority is the wedge and the highest is the dash, find out that spin and then just flip your answer. It is as easy as walking behind the molecule and looking at it from the other direction. So that swap rule helps us designate R and S configurations. And when we prioritize for the Cahn-Ingold-Prelog system, make a note that double bonds count twice. So if I'm trying to decide priorities and I see a double bond, for example, a carbon attached to a double bond oxygen, it's like counting oxygen twice. So you would have a Q that carbon is attached to. Double bonds give you twice the oxygens in that example. So double bonds count twice for the atoms they're attached. When assigning an R or S configuration, Cahn-Ingold-Prelog rule summary, we want to identify the 4 atoms directly attached to the chiral center. And we do so in order to assign a priority based on the atomic number. The highest atomic number receives the priority number 1. Highest priority is the highest atomic number. The lowest priority is the lowest atomic number. It's usually a hydrogen. It receives a 4. If 2 atoms have the same atomic number, move away from the chirality center looking for the first point of difference. When constructing lists to compare, remember that a double bond counts twice. Here is a chiral center. 2 of those 4 bonds lead to carbons. That's not a point of difference. So you can see that's a tie at this point. So we move away 1 spot further from the chiral carbon and see if we can find a point of difference. This carbon is attached to 2 other carbons and a hydrogen, so its list, CCH. This carbon is attached to a carbon and 2 other hydrogens, so its list is CHH. Here is the tiebreaker. This side is of higher importance, a higher priority than this side. And the last, if this carbon is attached to a double bond oxygen, remember to count it twice. Rotate that molecule to make sure the 4th priority is always behind the page, and just connect the priorities 1, 2, 3 and decide if it's spinning clockwise or counterclockwise. Let's practice. Determine the R or S configuration. Well, notice the chiral center will give you the stereochemistry information. I see dashes and wedges right there. The dash is the NH2 group. All right, so here is the chiral center right here. It has 4 unique attachments. Not shown, but we know is there, is the hydrogen as the 4th bond. So here's the chiral center. Right now as it's drawn, we have a hydrogen. I know that's going to be priority 4. We have a nitrogen and 2 carbons. So the nitrogen will be priority 1. It has a higher atomic number than a carbon. When I think about these directions, I'm leading up then to a carbon attached to an oxygen, 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 right? Counts twice. COO, that's 3 oxygens it's connected to. And when I move in this direction, I see the carbon is attached to 2 hydrogens and another carbon. So this becomes the next highest priority, and this becomes the 3rd highest priority. So right now, that's our spin for this particular molecule. We had lowest priority as the hydrogen, assigned number 4. It's sitting on a wedge right now. The highest priority is sitting as a dash. Notice now we meet that criteria of highest is a dash, lowest is a wedge. So you can find the spin as it sits now and just flip your answer. And we can prove this 2 ways. So right now, if I were to connect 1, 2, 3, I'm spinning in a clockwise fashion, which is the R, but I know I'm standing on the wrong side of the page. So I'm going to flip my answer to the opposite answer, to the counterclockwise, and I know now that that's an S configuration. We can prove it to ourselves. Let's swap 1 with 4. First swap, let's swap 1 with 4. And so now 1 is coming out as a wedge, 4 is going back as a dash. Swap 1. The first swap, we swapped out 1 with 4. But now that's the enantiomer. That's not what we want to end with. We don't want the mirror image. We want the same molecule back. So we need a second swap. Leave 1 and 4 where they are, and now swap 2 with 3. Swap 2 and 3. So now we get 3 and 2 in this direction. Now when we connect 1, 2, 3, I can see the counterclockwise spin, and yes, we've proven with 2 swaps, we're able to prove to ourselves that that's the S configuration. You can literally walk behind the molecule and look at it from the other direction and see that when this is the wedge, you just simply flip the direction. So we decided that's an S conformation. You can use the swap rule for a lot of skills, such as asking yourself, are these the same or are they enantiomers? A lot of your homework just simply asks, are these the same or enantiomers? Are they the same or mirror images? And using the swap rule, remember, swap just 2 at a time and see how long it takes to create the first into the second. So for instance, here's a chiral center, and I see that I have 4 attachments. Let's label those in terms of priority. Right now, the highest atomic number is bromine, so that's priority 1. The lowest atomic number is hydrogen, so that's of lowest priority 4. The next highest would be chlorine, and then finally the carbon. So in order of atomic number, we're assigning priorities. Now let's see what we have. Here's the bromine, here's the chlorine, here's the hydrogen, here's the methyl. Are they the same or different? How many swaps does it take to convert one into the other? Well, first thing I can do is, let's see, chlorine, he needs to move. Bromine stays where he is, right? So bromine looks like the only thing that I don't need to swap. Methyl, let's swap. For the first one, let's swap 2 with 3. And then let's redraw. So this is the original. This is our first swap. So let me redraw. I have the carbon here. And now all of a sudden I'm going to swap for chlorine here. Methyl came up, and that's where I wanted it. And then, of course, bromine stayed the same, as did the hydrogen. All right. So swap 1. I've got the methyl group where I want it. I've got the bromine where I want it, but the Cl and the H are not yet the same as the second structure. So we're going to need a second swap. And when we do so, in the second swap, we're going to switch priority the chlorine. Well, I should do it this way. This is still 3. This is 1, 4, 2. Switching those priorities. Just make sure you keep them numbered, because now when I swap, I want to swap priority 2 and priority 4. And when I do that, I'm going to swap these two first. First swap, Cl and CH3. Second swap, the chlorine and the hydrogen. And when I redraw that swap, I've now created the same molecule as the target. So this was the enantiomer in the first swap. This was the same molecule in the next swap. So these two are the same. It took an even number of swaps, 2 swaps, and I was at the same molecule. Are these the same or enantiomers? Chiral carbon in the center, priority 1 is the bromine. Priority 2 would be the chlorine. Priority 3, the fluorine. Priority 4, the hydrogen. How many swaps would it take to convert one into the other? Well, let's see. Hydrogen looks to be on a straight line, so I'm not going to choose to move him. Fluorine, bromine, yeah, we've got some swapping. So let's take a look. Let's swap, I don't even know where to begin. Let's swap chlorine and bromine, see what we get. First swap. This becomes the bromine. This becomes the chlorine. Here's the hydrogen. Here's the fluorine. Swap 1. We're not there yet. Let's do another swap. Let's swap. We need bromine to be the wedge, so we got to keep going. Let's go again. I'm going to put the hydrogen up here, the bromine down here, the fluorine here, chlorine here. Swap 2. So here's the enantiomer. Here's same. Not there yet. We need bromine to be on the wedge. Keep going. Next swap. This would put bromine on the wedge, and it would put, I didn't draw that right. Here, this would be fluorine. This would be bromine. This would still be chlorine. And this is hydrogen. Did we do it? This is swap 3. Carbon has a straight bond to hydrogen. It does. Straight bond to fluorine. It does. In the same plane as the carbon are the H and the F. Yes. Coming out of the page as a wedge is a bromine. Perfect. Going behind the page is a chlorine, as a dash. Perfect. All right, so we've accomplished it. It took us 3 swaps. So enantiomer, same, enantiomer. After 3 swaps, we determined that those are non-superimposable mirror images. Woo, we did it. I feel accomplished. How about you? When we use the R and S configuration and just kind of going through the swap rule to determine if it was spinning clockwise or counterclockwise, I introduced a little application of saying, you know, I can use the swap rule to determine the configuration of R and S to determine if it's the same or an enantiomer. It becomes part of the name written out front, just as we learned that cis and trans do as well. An R configuration, we would have R-2-butanol. And the opposite configuration, we would see S2-butanol. If you have 2 chiral centers, you now have to give them numbers along with the R and S. 2 chiral centers, I know that this would be 1, 2, 3, 4, 5 in the numbering system. The first chiral center has an R configuration. The second would have an S configuration, and you'd simply then name the compound. 3-methyl, 2-pentanol, knowing that alcohols will get the priority when naming. At chiral center 2, we have an R configuration. At chiral 3, we have an S configuration, and then the rest of the name as usual. You know, when we think about enantiomers, these non-superimposable mirror images, they have identical physical properties in the following categories: melting points, boiling points, refractive index, solubility. They really are twins. These enantiomers have many things in common. What is unique about a chiral carbon and its non-superimposable mirror image is how they rotate light. Chiral molecules are optically active. Because these structures differ only in the way that they spin light, they are very similar in terms of physical properties, with just one exception: how they interact with other chiral compounds in a biomedical pathway, if you will, or, in the second example, is the rotation of light. Let's examine optical activity. Remember, enantiomers, these non-superimposable mirror images, react differently in biochemical pathways and how they rotate rotate light in a polarized plane. Chiral molecules are optically active. One question you might hear in a homework example: is this a compound that is optically active or not? And they're really just asking you, are these compounds chiral or not? So don't let that other way of asking the same question fool you. All chiral compounds are optically active. Now, examining what that means, let's suppose we have a light source, just a white light, and all the wavelengths come out of a light source, and it goes through this polarized lens. A polarized lens is like a diffraction grating where all of these slits are in the same parallel direction. So what that will do is turn this omnidirectional wavelength into the same parallel lines. Now, when you see that looking through a polarimeter, you would only see the lines as going vertical. That's like a diffraction grating. However, if we had, an opportunity to place a sample of a chiral molecule before your vision, you'll notice that it rotates light. So let's get an idea of what this is. This is the source of light. It's omnidirectional, all wavelengths at once. When it hits a diffraction grating, notice this is just a polarized lens. The only light now that's allowed through this polarized diffraction grating is in the same plane as that lens. When the light now passes through a chamber that has a chiral molecule in it, the light is going through a chamber, and what happens is that the priorities of those molecules around those chiral carbons are going to cause a rotation of the light. So as the arrows indicate, the optically active substance in the solution is causing what was originally in a vertical line is starting to rotate. And as it rotates and comes out of this chamber, you're actually able to measure how far the light has rotated. So if this was the original 0-degree angle, perhaps it's going to rotate negative 90 degrees to the left or positive 90 degrees to the right. We measure the change in direction of the polarized light angle. So chiral compounds are optically active. An important note: optically active does not mean I can tell if it's going to spin R or S, or if it will spin positive or negative. They're not correlated. But I can tell you that enantiomers spin light equally, but in the opposite direction. So R and S are the letters that we use to designate configurations, knowing that the R configuration would spin in a clockwise, and the S configuration tells me that the priorities are going in a counterclockwise. It has nothing to do with the direction that the light will spin. There is no correlation. I cannot know that an R will be negative. I cannot know that an S will always be positive. There's no correlation. So every time we have to test in the lab with a polarimeter to decide if the configuration will spin positive or negative. And we should know these vocabulary words as well. Know these: that the dextra rotary is the positive rotation and the levo rotary is the negative rotation. It has absolutely no correlation with being R or S. The only thing we know for sure is if the R, let's say, spins positive 20 degrees, the S will do exactly the same thing in the opposite direction. It'll be a negative 20 degrees in terms of rotation from the zero. Negative 20, positive 20 in terms of rotation of the bond angle. Chiral carbons are optically active. I have no correlation in knowing if an R will be positive or negative, if it will be dextrorotary or levorotary, but I do know if I can figure out what one is doing, I can determine what the other is doing by opposites. The magnitude and direction of optical rotation cannot be predicted, but has to be measured experimentally. Of course, if you have a racemic mixture, which is 50-50 of both enantiomers, if I have an equal amount going through that polarimeter, I would have one set of molecules spinning the light in this direction and the other set of molecules spinning it in the opposite direction, all equal, not in excess. Then I would have zero rotation overall. Zero rotation because each would cancel each other out. In this example, we're emphasizing vocabulary words and really just kind of driving home some things that we've been saying. So enantiomers versus diastereomers. Remember we started with a review of isomers? Isomers fell into two categories, constitutional isomers and stereoisomers. Constitutional isomers, those molecules that are the same, they just have same molecular formula, they're just attaching their atoms in a different order. Butane and 2-methylpropane are examples of constitutional isomers. Those molecules that have the same connectivity, but connected in a three-dimensional difference, connected in space differently, are known as stereoisomers. Stereoisomers can be one of two categories. They can be non-superimposable mirror images, known as enantiomers, or they're not mirror images at all, and we call those diastereomers. For example, a cis and a trans are diastereomers. We can see that they are not mirror images at all. They are indeed connected in the same order to butene. To butene, we have 4 carbons bonded in the same order, and yet spatially they are very different. If these are on the same side of the pi bond, we're learning to call those cis, and if they're on the opposite side of the pi bond, one group here, we've learned to call those trans. Clearly they are stereoisomers. Those are atoms that are bonded in the same order, but in a three-dimensional way, they're not connected in the same. So they're not mirror images, diastereomers. Diastereomers have different physical properties. Mirror images, such as enantiomers, have exactly the same physical properties, except that they don't spin light in the same direction. So thinking about that, enantiomers and diastereomers becomes more and more relevant when we consider compounds containing more than one chiral center. And that's what we have to think about in terms of a meso compound as well. I'm going to break the video here and come back and talk about compounds that have more than one chiral center and introduce a vocabulary word known as a meso compound.